Hello everyone, welcome to CSCN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mogi. In our previous lecture, we had started a discussion about the application layer. So we're going actually down the layers of the protocol stack, starting with the application layer, and we will proceed in the remaining lectures of the course with the other layers. So in the last lecture, we studied the main application protocol architectures that we find, client-server and peer-to-peer. We discussed also the most important protocol we find in the application layer, which is HTTP. We discussed the structure of HTTP. How does HTTP actually open TCP connections, persistent and non-persistent connections? And the last topic we discussed was cookies. Today we are continuing our discussion of the application layer. We have one more topic to discuss about HTTP, and then we will proceed to discuss another protocol that we find in the application layer, which is DNS, or the domain name system. Last time we said that HTTP is actually a stateless protocol, meaning that if you send actually 10 HTTP requests to the same destination, you will actually get 10 responses, even if this request, or if these requests actually contain the same URL. Meaning that the server which saves the content doesn't save any information about you. This is of course separate from the cookie system, which allows actually the server to save information about the client. However, the normal, or the, let's say, blank or the default HTTP protocol does not actually allow the server to save any information about the client. We also said that the bottleneck in the delay between the client, if this is the client and this is the server, the client will open a TCP connection, so that's one round trip time, and then we'll start actually sending HTTP requests and receiving responses, and each request response pair is a single round trip time. And we said that the bottleneck in the delay is not actually the speed at which the client or the server will send these requests. It's not actually the transmission delay that is causing the problems. It's in fact the round trip time. And the round trip time, as we said, is the total time needed for a small packet to reach the destination and for a response to come back. And so it's a factor of how many routers there are between the client and the server, the geographical distance between the client and the server, which of course influences the propagation delay. It's a factor of the transmission delays of the router, of the processing delays of the routers, and of course of the queuing delays of the router. So the client and the server really have no control over the round trip time. They cannot actually decrease it. And this then becomes the bottleneck in any communication between the client and the server. Meaning that if an application provider, like Facebook, for example, or Amazon, want to reduce actually the delay that a client sees, they will not be able to, because they cannot actually manipulate the round trip time. Also, if internet service providers want to provide you with a good performance, they want you to think that their internet connection that they are providing you is one with a good quality, they will want you to actually have a reduced delay experience, meaning that they want you to be able to download pages quickly. And of course, they too cannot control the round trip time. So what is the solution for that? The solution is what is called a web cache or a proxy server. A web cache or a proxy server is usually implemented by the organization that serves the client. This can be the organization that the client belongs to, for example, something like the GUC, or it can be the internet service provider itself. So the proxy server is nothing but just a normal server that temporarily saves resources on behalf of clients. So let us actually see how it works in order to understand what is the purpose. If there is a proxy server in my network, once I actually establish a TCP connection and send an HTTP request, I do not establish the connection with the origin server anymore. I will actually establish a TCP connection with the proxy server, and then I will send my HTTP request to the proxy server, and then the proxy server will establish also a TCP connection with the origin server, and then send the HTTP request to the origin server. The origin server is where we want to download the content from. Server response, it will respond to the proxy server, okay, and then the proxy server will keep a copy of that page in its cache, in its temporary memory, and will forward another copy to the client as you see here. So now the client actually has the resource, whatever it is, and the proxy server also has another resource. Now, so far, there is no actually advantage to the client. In fact, there is probably some additional delay because there are two TCP connections that have been established, two HTTP requests, two HTTP responses. However, because the proxy server is usually or is always located in the same network as the client, the round trip time between the client and the proxy server is usually very small, and this delay is not a significant one. This is actually not just the end of the story. Now we can see actually the advantage of the proxy server. If another client in the same network wishes to download the same resource, they will actually follow the same procedure. They will establish a TCP connection with the proxy server, send an HTTP request and receive the response. But now the proxy server actually has a copy of that resource because another client has already requested it. And so the proxy server will be able to respond directly without going again to the origin server. And so the client will save itself a round trip to the origin server to retrieve the resource. And because, as we said, the round trip time between the client and the proxy server is much, much less than the round trip time between the client and the origin server, the second client will end up saving a lot of time. And so if there are more clients in the network, they will all be fetching the same resource from the proxy server, resulting in significantly less delay. And so these clients will see an excellent level of performance because the delay will be very low. So they will think that their ISP is actually doing a great job in providing them with content, but in fact, it is due to a cache or a proxy server that is saving content and forwarding them to other clients with a short round trip time. So now there are several actually questions. The proxy server will typically receive many HTTP requests and receive many HTTP responses on behalf of the clients from different origin servers around the world. Now the question becomes, which objects should actually the proxy server save? Because it's a cache, it means that it's a temporary memory. It means that any resource will be saved for a period of time. If no one actually requests it within this period of time, then after the period of time expires, it will be deleted from the proxy server. And if it is deleted from the proxy server, then a client that requests it again after it has expired, the same process will have to be followed. That means the proxy server has to fetch it again from the origin server. Now, which objects should the proxy server save? The answer to this question is that the proxy server should actually save the resources that are most likely to be requested by more than one client, because then this becomes an efficient process. Each object that the proxy server saves consumes a space in the memory, consumes a space in the cache. And because it's a limited space, the proxy server would want to use this space in the most efficient way. And so it is best that the proxy server would save the objects that are actually going to be used by a larger number of clients so that these clients would benefit from the saved object. If you save a resource and no one else requests it, then this is actually a wasted cache space in the proxy server. So usually proxy servers will have something like a popularity count. When an object becomes requested by more than one client, this is an indicator that this object or this resource is something popular that should actually be saved, and the proxy server will save. That being said, normally proxy servers are wasteful. That means it is more than normal that proxy servers or web caches will actually save content that are not often used by the clients. It's just the way it is, because at the end of the day, the traffic in the internet is random and no one can actually know in a deterministic way what the client will actually request. So the best thing that the proxy server would do is to think what kind of objects are most relevant to that organization. For example, if it's the GUC network, then most likely the proxy server would want to save some resources related, for example, our partner German universities, or the IEEE website, or something that clients in this network will actually request often. Another thing is that proxy servers usually do not save dynamic or customized content. If a client, for example, is downloading their Facebook page then obviously it doesn't make sense for the proxy server to save a copy of that person's timeline, that person's customized news feed, because this is of no importance to anyone but the client. But what is actually of relevance, the background of the page itself, that is the same among all the Facebook users, is something that is worthy to be saved. For example, the Facebook logo, the HTML file of the page itself. All of these are resources that are common across the different users, and it is then worthy for them to be saved. Another important issue is that proxy servers usually do not save dynamic content that usually are changing frequently in the origin server. They are updated frequently, like, for example, breaking news or something like that. And so the proxy server would most likely save items that are static, things like images, like videos that will not actually change, and are resources that are considered to be popular with the clients, are something that are examples of objects that are worthy to be saved. Okay? This is, let's say, the overview of how the web caches and the proxy servers work. Now, what we want to do is take a look at a numerical example and see how much savings in delay we can actually get with web caches. So consider the network that you see on the right here. You have an institutional network. So you have a bunch of clients, as you see here, client 1, 2, 3, and 4, and they are all connected to a switch. When you see an Ethernet network like the one that is shown in the figure here, that connects actually four clients, then this means that there is a switch, and then the switch is actually connected to the router, the first router here. Let's call it R1. Okay. Now, let's say that the speed of this local area network, the institutional network that is connecting the four clients to the switch and the router, the speed there is 100 megabits per second. And then there is an internet connection between R1 and the second router, which is R2. And this internet connection has speed 15 megabits per second. That means that this 15 megabits per second is actually shared among all the institutional clients. Okay. And then you have the public internet, where there are many origin servers connected. So the only way clients 1 to 4 can access the internet is through R1 and R2. So the assumptions in this example say that the clients are generating objects, or they are requesting objects, and each object has size of approximately 1 million bits. And the clients generate in total 15 requests per second. So they are generating total, the four clients are generating a total of 15 requests per second. Each request is actually requesting an object that has 1 million bits. Okay, and the delay from the internet router, which is R2, okay, the delay from R2 to any origin server in the public internet, so the delay from R2 to an origin server and back, is actually approximately 2 seconds. So we want to calculate, let's say, how, or we want to get an image about the delay in this network. How will the delay be? Will it be a high value? Will it be a low value? How exactly will it be? To calculate that, we already know a metric that we didn't explore in depth, but it's actually a very useful one, which is the utilization. If you remember our discussion of packet loss, we said that if you have a router, and the router is actually receiving packets across all its ports, and each packet has length L, and the router is receiving A packets per second, okay? If LA is greater than the speed of the router, that means the incoming traffic is greater than the outgoing traffic, then it means that the router will become congested. This is actually the utilization metric. So the utilization is nothing but LA over R. What is incoming over what is outgoing. So we want to calculate the utilization of all the connections that we have in this figure in order to figure out where are the links that will be congested, and the links that are congested are expected to have high queuing delay, and so high overall delay in total, and which links will be considered to be not very congested. We start with the link between the clients and R1, okay, the institutional network. We calculate the utilization over R1. So these four clients will be generating a total of 15 requests per second, and all these requests would like actually to download a resource from one of the origin servers in the public internet. And so there is no other way for these requests to download these resources, except that they have to go through R1. So all the requests end up making their way through R1, and all the responses end up coming back from the public internet to the 4 clients through R1. We are saying that there are 15 requests per second, and each request is 1 million bits. So the utilization of the LAN is LA over R. L here is the length of each packet, and we know that the size of each object is 1 million bits. So L here is 1 million. A is the number of packets that are arriving per second, and which is equal to the number of requests. So LA is 15 requests per second multiplied by 1 megabits per request. 1 megabits is just 1 million bits per request. Over R, and R here is the speed. And we know that the speed of the institutional network is 100 megabits per second. So this is 15 requests per second multiplied by 1 megabits per request over 100 megabits per second, which gives us a utilization of 15%. That means LA is significantly less than R. A utilization of 15% is low enough, which means that R1 will not actually be very congested. Now we take a look at the 15 megabits per second link, and we do the same. So now we calculate LA over R again. What is L? The same object size, which is 1 megabits per request. A is the same traffic, which is 15 requests per second, because all these requests end up being sent from R1 to R2. So we're having 15 requests per second multiplied by 1 megabits per request. But now the speed is 15 megabits per second. And so we have 15 multiplied by 1 megabits per request over 15 megabits per second. We end up having a utilization of 100%, which is actually a very high utilization. So the total delay will be the delay in the institutional network, the LAN, plus the access link, plus the public internet. Okay. The delay in the public internet is a fixed one. We're saying that it's about 2 seconds. The delay in the institutional network, the local area network, will be on the order of milliseconds because LA is significantly less than R. The utilization is 15%. So this will probably have a very low delay. However, the utilization over the access link will be on the order of minutes because the utilization is 100%. So we can say that the bottleneck link in this network is actually the access link, which is having a speed of only 15 megabits per second. And so it ends up having high queuing delay. So what is the solution for that? If this is actually the bottleneck link, then what we can simply do is upgrade it. Instead of actually having 15 megabits per second, you can just actually upgrade it to 100 megabits per second. And if you recalculate the utilization values with the same assumptions, the utilization on the LAN doesn't change, so it's still 15%. It's still the same LA over the same R. The utilization on the access link is now 15% because now R, which was 15 megabits per second, is now 100 megabits per second. So it's 15 requests per second multiplied by 1 megabits per request over 100 megabits per second, which will give you 15%. And so now the utilization over the access link is also very low. And so the overall delay will end up being very low. However, what is actually the problem with this solution is that the upgrade from 15 megabits per second access link to 100 megabits per second is probably a very costly upgrade. Imagine actually buying an internet connection at home and compare the price between 15 megabits per second and 100 megabits per second. Most probably it's significantly higher, and it's also a recurring cost. It's something that the institution would have to pay every month forever as long as they're actually using the internet. What is the other more cost-efficient solution? Is to actually invest some capital into buying what is called a web cache or a proxy server. And the web cache will be installed in the institutional network. Okay. Each web cache has a metric or a parameter that is associated with it, which is called the hit rate. The hit rate is actually nothing but the average number of requests that the web cache can satisfy. So if we're saying that the hit rate is 0.4 or 40%, that means 40% of the requests will be satisfied by the web cache, and the remaining 60% will not actually be found in the web cache. And so the web cache has to forward them to the origin servers and get the response from there, just similar to what we were actually saying in this figure. Okay. So now these 4 clients, instead of actually sending their requests to the router R1 and then to router R2 and then to the origin servers, they will be sending now their requests to the web cache. Okay? Of course, they have to establish a TCP connection first, but we already know that this is always done. So they will be sending their request to the web cache. If the web cache has the resource, they will actually reply directly, meaning that the request that will be responded to directly will never actually leave the LAN. Okay. And if it is not found in the web cache, then the web cache has to forward it to R1 and R2 and the origin server and receive the response. So what will be the delay in this case? This is actually the exact same network as the first one, this one that we were discussing, same parameters, so same 15 megabits per second access link. However, here we were saying that the utilization on the access link is actually 100%. This is because all the 15 requests per second end up making it to the access link, because there is no other way. There is no web cache in this example. Okay? If there is a web cache, and we are actually saying that the web cache has hit rate 0.4 or 40%, then 40% of the requests will actually be responded to from the web cache directly, and the remaining 60% will end up being transmitted over the access link. That means the utilization over the access link is now 60% of what it was. It used to be 100% if there is no web cache. Now it is only 60%. That means the utilization is 0.6 or 60%. This is also an acceptable utilization because it means that LA is also less than R. And so you end up having a smaller delay over the access link. So with the web cache, you're able to reduce the overall delay again to something on the order of milliseconds or at least a few seconds, not something on the order of minutes as we saw in the first example. This is actually what web caches do. Now, one remaining question about web caches is that if you are actually getting the response from the web cache itself, how do you know that this object that you're downloading from the web cache has not actually been changed in the origin server? That means, for example, let's say a company like Facebook has decided to change their display, and you're still actually getting the response from the web cache, and so you will not be getting the, let's say, the updated display that has already been saved on the origin server but has not been saved in the web cache yet. HTTP has a header line that supports that. If you include in your HTTP request the header line, if modified since, and then enter a particular date, then the server will respond with either an empty response with the status code 304 not modified, meaning that the object that is requested has not been modified since the date that was mentioned in the request. Or if it has been modified, then the response is going to be 200 OK, and the new object will be sent. That means the web cache, if it wants to check that the object has been updated, it can actually send an HTTP request and include the if modified since header line. And so if it has been modified since that date, the new object will be sent. If it has not been modified, then an empty response will be sent. Now, if the web cache is going to be sending this request response pair anyway, then what is actually the savings in delay in this case? The answer is that the web cache will not actually send this message often. And if the object has not been updated, then it will get actually an empty message, which will not actually consume a lot of bandwidth resources. Okay. This is then the end of our discussion of the web cache system, and it's also the end of our discussion of the HTTP protocol itself. Now we are going to start discussing a new topic, and it is going to be the last topic of the application layer. It's actually another protocol. It's a little bit more than a protocol. It's a complete system in the internet that is called the domain name system. And the domain name system is one of the most important systems in the internet. Without it, we will not actually be able to download any web page and will not actually be able to use HTTP at all. When we were discussing the protocol stack, we said that we can actually have an example where we have, here we have our layers. That's the application layer. That's the transport layer. That's the network. That's the data link layer. and this is the physical layer. We said that the network layer is the one that is responsible for adding the network layer header, which includes the IP addresses. So the message M is generated at the application layer. It is sent to the transport layer, which adds the transport layer header, which includes the port numbers. And then the message plus the transport layer are given to the network layer, which adds the network layer header, which includes source and destination IP address. Okay. So the source IP address is given to the device. Let's say this is client 1. The source IP address is given to the device by the network itself, by the ISP basically. If you are connected to a Wi-Fi router at home, then the Wi-Fi router will be the one that is giving you a source IP address. Where does the destination IP address come from? This is something that we have not answered yet. And the answer to that is actually the domain name system. The domain name system is a global database whose main responsibility is to provide a translation from a URL to an IP address. Basically, in the application layer, let's say, for example, a user is on their browser and they enter a URL, for example, www.facebook.com. When the user enters this URL and clicks enter, then an HTTP request will be generated at the application layer, at the HTTP protocol level. And this HTTP request is going to include the URL of Facebook, facebook.com. And now, in order for this request to be sent, client C1 that is actually generating this request has to know where the request is going to be sent, has to know what is the destination IP address of this Facebook server. And if the Facebook server actually has many servers around the world, then the client needs to know one IP address of one of these servers. The domain name system is the database where this IP address is retrieved from. Okay. So it's a database where you actually submit to it what is called the DNS query. This DNS query includes the URL that you want to translate, and the response to the DNS query, which is the DNS response, includes the IP address of the URL that you are asking for. Okay, so it's a translation mechanism that translates URLs to IP addresses. So let us now think about the design of this domain name system. First of all, can this system ever be centralized? The answer is obviously no, because if it is actually a centralized network, that means there is one huge database that is saving all the translations of all URLs to IP addresses. This, first of all, will become too huge to even maintain. And more importantly, it will become a single point of failure. If this database fails, there will be no translations from any URLs to any IP addresses around the world. So no one will actually be able to access the internet. So best to have it as a distributed database, where if one database system fails, the others will be still operational, and you will still be at least translating some URLs to IP addresses. For example, a few years back, there was an attack on a huge DNS database. I think it was in the US, and it brought this database down. And so for a period of time, all the URLs that were saved in this database were not accessible. And some of them were big, actually, websites like I think Amazon and Microsoft. And so for a while, these websites or these URLs were not accessible because no one was able to translate actually their URL to an IP address. Okay. What other services does DNS actually provide? So it is, of course, a distributed database that translates a URL to an IP address. So it will be a database that has, for example, 2 columns. Here you have a URL and its corresponding IP address. And so if someone asks for this IP address and sends them the URL, it can actually respond back. This is called host name to IP address translation. This is actually the main service. We said that big organizations will have what are called server farms, huge data centers that have a very large number of servers. And so at the end of the day, your request will end up making it to only one of these servers. In fact, these servers, actually, each of them has a slightly different URL. For example, you have something called facebook.eastcoast.so-and-so. we as regular human users do not know these real URLs. You only know what is called the canonical, the alias URL. The canonical is the real one, the longer one, facebook.eastcoast.com, for example. The alias is the one that we are more familiar with, just facebook.com. The translation from canonical URL to an alias URL is also done by DNS. It does that for regular websites, and it does that for mail servers as well. So if you have, for example, the mail server of the GUC, if there is more than one, and each one has a different URL, you can actually just use guc.edu.eg, and you don't have to know the canonical URLs of each server. Another very important service related to this issue is what is called load distribution. If Facebook has actually a large number of servers, okay, how are these servers going to be accessible? So server 1, server 2, server 3, how are these servers going to be accessible to the clients? The answer is that the IP addresses of all these servers have to be saved in the DNS database. They have to be saved in a distributed database. Not every server in this DNS database has to save all the IP addresses, but each one saves a portion. Okay? So all of these IP addresses of the Facebook servers, they actually have to be saved in the DNS database. Because they are all saved in the DNS database, the DNS is also able to help the Facebook organization by doing load distribution. Therefore, what the DNS system would do is that if you have several clients requesting all of them the IP addresses of Facebook servers, the DNS system doesn't have to return the same IP address of the same server each time. It means the DNS can rotate actually over the IP addresses that it has, thereby returning a new IP address of another Facebook server each time it is requested. In practice, this would mean that a new request will actually be making it to a different Facebook server each time, therefore achieving load balancing over these servers. So it's sort of a round-robin fashion where the DNS will actually return a new IP address to a new client each time. So the request will be sent to a new IP address, thus distributing the load over all the DNS servers. Okay. So these are the services. The DNS system is a distributed database. Now we can actually take a look at more in-depth details about the DNS. It's not only distributed, it is actually also hierarchical. Okay. There are 3 layers of the DNS hierarchy. The top layer is called the root DNS. The layer below is called the TLD, or the top level domain DNS. And the last one is called the authoritative DNS service. So any DNS server is one of these 3 types. It's either a root DNS server or a TLD or an authoritative DNS server. What is the meaning of all of that? Imagine that you're actually going on a trip from New Cairo to Maadi, for example. You want to go to a very particular street in Maadi and you don't know it. Let's say that you don't also have Google Maps. So what you will do is that you will stop and ask for directions. You will ask someone, how do I get to this street in Maadi? They will tell you, well, I don't know the street, but I know how to get to Maadi. Let's actually just take the 90 Street and then go to the area. Okay. You do that, you go to the area, and then you ask someone else, how do I get to this street in Maadi? They will tell you, I don't know, but you have to take this exit because this is where Maadi is in general. So you go and take this exit, and then you ask another one, and then ask another one, until someone actually knows exactly which street you are looking for. This is roughly how the DNS database works in a hierarchical way. At the top, you have the root DNS servers, and the root DNS servers don't actually have the IP addresses of any website. They actually have the IP addresses of the top level domain servers. The top level domain servers are responsible for domains. So there is a server responsible for everything that is .com. There is a server responsible for everything that is .org, .net, .edu, .edu.eg, .edu.uk. Okay, so when you want to resolve, let's say you want to resolve Facebook.com. The first thing your device will notice is that this URL ends with .com. So it will go and ask the root name server, the root DNS server, and it will tell it, I have a URL that ends with .com. Please give me the IP address of a TLD server that is responsible for everything .com. So the root DNS server will tell you, okay, I have actually this top level domain server. This is its IP address. Please go ask it. So you will then go ask a top level domain server that is responsible for everything that is .com. This one will have, for example, entries for Facebook.com, Amazon.com, but not the IP addresses of the URLs itself, the IP address of an authoritative name server that knows the IP address of this URL. Okay, so you will go and ask the TLD, and it will give you the IP address of an authoritative name server, and then you go and ask it, and it will give you the IP address of an actual server that you can access. Okay, so the root name server gives you an IP address of a TLD server. The TLD server gives you an IP address of an authoritative server, and then an authoritative server will give you an actual IP address of a web server that you can access. You have to note that all of this is done before any TCP connection is established with the destination, before any HTTP request is sent to the destination. And this makes sense because you don't yet have an IP address of the server, of the web server, of the Facebook.com server, in order to send it anything. So this process has to be finalized, the DNS process has to be finalized before you're actually able to send any TCP connection request or any HTTP request. This here shows you actually a map of the root name servers. There are 13 root name servers around the world, and you can see where they are located. These are major databases that saves the IP addresses of the domains. The nice thing is the domains are not too many, and so their update is not as frequent as you have URLs for just regular websites. Okay. One missing item in this picture is called the local name server. So far, we're saying that the client is the one that is trying to resolve the URL. The client is the one that is actually trying to translate the URL into an IP address. The client doesn't actually do this on its own. The client does that through something called a local name server. And the local name server is a part of your ISP, and it is the server that is responsible for resolving the URL into IP addresses on behalf of the client. To understand how this works, we should actually take an example. So let's say you have the requesting host here that is trying to send an HTTP request to this device, gaia.cs.umass.edu. It doesn't know its IP address, and so what it will do is it will access the DNS database in order to translate the URL into the IP address. Be aware that we assume that the URL is known. If the URL is not known, then you have to go through something called a search engine or something like that actually finds the URL for you. But we are assuming that the URL is actually known. So the first thing the requesting host will do is that it will send a DNS query to the local DNS server, including the URL that it's trying to translate. This local DNS server belongs to the ISP of the requesting host. Now, the local DNS server will take a look at the URL and find that it ends with edu. And so it will send a query to the root DNS server saying, I have a URL that ends with edu. Please give me a top-level domain server that is responsible for everything that is .edu. Okay? And so the root DNS server will respond with an IP address of a TLD name server. The DNS servers are called name servers. And then the local DNS server will then send another DNS query saying, I have something that is ending with UMass or cs.umass.edu. Please give me an IP address of an authoritative name server that is responsible for that. So the TLD name server will respond with the IP address of an authoritative name server that can be accessed. Okay, so the local DNS server will send another DNS query saying, please give me the IP address of gaia.cs.umass.edu, and the authoritative name server will respond. And then finally, the local DNS server will send back the IP address to the requesting host. After all this is done, the requesting host can then send a TCP request to the destination, get a TCP response, and then send an HTTP request and receive an HTTP response. You have to note that all of this, TCP and HTTP, is not part of the DNS system at all. The DNS process has to be resolved completely before the requesting host can send anything to the destination. You also have to note that the DNS system does not receive HTTP requests. So you don't send an HTTP request from the requesting host to the authoritative server. It will not understand it. These servers, the name servers, the DNS servers, are using the DNS protocol. They only understand queries and they send responses. They don't understand an HTTP request. Another common mistake that students quite often do is that they imagine or they get confused that the HTTP request is sent from the requesting host. Sometimes they think that after the authoritative name server receives the query in step number 6, they will then forward an HTTP request to the destination. The authoritative name server will only reply to the local DNS server. It will never actually forward an HTTP request to the destination. Everything that belongs to the DNS system is only part of the DNS system. They will never actually send anything related to HTTP. Okay. This figure here shows you something called an iterative query. The iterative query is or has the local DNS as its center. It's the one that receives the original query from the requesting host and sends all the queries to the other name servers and receives the responses. There is another type of query that is available in DNS, but it's not as common as the iterative query, and it's called the recursive query. Here again, the requesting host will send the DNS query to the local DNS, which will send a query to root DNS. But instead of the root DNS replying directly to the local DNS, it will forward it to the TLD, and then TLD forwards it to authoritative, and the response comes back from authoritative in step 5, TLD to root in step 6, root to local in step 7, local to requesting host in step 8. This is less common. It distributes the load across all the servers, but it is less common because it's actually more desirable to have the load centered at the local DNS rather than distributing it around the other servers. The reason is that the local DNS is only the responsibility of the ISP, while the root TLD and authoritative DNS servers are shared among all the clients around the world. And so they are receiving much higher traffic than the local DNS server. They are receiving much higher DNS queries than the local DNS server. So it's best actually to have the load more on the local DNS server and not distributed over the other DNS servers because they are already overloaded. The other important issue is all of these servers have caches that store any translation that passed through them. That means if the local DNS server receives a translation for a domain that is .edu, it will not actually go and ask a root DNS server for something that is .edu another time. That means if you're trying, for example, to access guc.edu, you already have the translation that is .edu. That means you know already the top level domain server that is responsible for .edu. So you don't have to ask the root DNS server for it. The local DNS will have cached it. Okay? All the DNS servers will cache the translations that pass through them, whether they are in their own hierarchy or not. That means the root DNS may actually cache an entry for an authoritative DNS, and the TLD may cache an entry for a root or the authoritative one. Anyone can actually cache any entry that passed through them. And so it is not necessarily the case that these full steps will be executed every time. It's actually quite unlikely that you will access the root DNS server at all. Only a few times you will need to access the root DNS server because the domains are common, meaning, for example, most URLs end in .com, .org, or .net. Okay? And your system, your local DNS will have definitely cached them before. So you rarely actually go to the root DNS. Same thing for TLD. Authoritative is the one that you will actually probably need to access more. And that's why there is actually a much larger number of authoritative DNS servers than there are TLD and okay. These cache entries will expire every 48 hours or so if no one requests them. This is actually the nature with any cache The entries expire if they are not accessed frequently. Last thing we will discuss today, we'll take actually a numerical example to see actually the effect of the caching in a DNS hierarchy. So let us actually read the example and try to solve it. So consider the network diagram on the right depicting three hosts, H1, H2, and H3, as well as three levels of a hierarchical DNS servers. So you have DNS 1, 2, and 3. The three hosts perform a large number of domain name lookups over the course of a day. When a given DNS requests in a zone of a name server, this means the server can resolve the domain name directly. In other words, it doesn't have to propagate the request to the next level. That means if a DNS server receives a query and the query is in its own zone, it can respond directly and it doesn't have to forward the request to the level above it in the hierarchy. So imagine, for example, that host H3 is issuing DNS request to DNS3. We say that the probability PZ of that request being in DNS3 zone is 17%. Okay, when the expected number of requests in DNS3 can resolve directly is 0.17 of the total number of requests. That means 17% of the requests are in the zone of DNS3. That means DNS3 has already saved them in its database, not cached. That's actually permanently in their database. This in turn means that 0.83 of all requests of DNS3 have to be propagated to DNS2. Furthermore, DNS2 and DNS3 perform caching. If, for example, the hit rate of a certain cache, denoted by CHR, is 1/10, this means that on average 1 in 10 requests be resolved from that server's cache. The other 9 have to be resolved by propagation, meaning propagated to the next server. Consider the table containing the probabilities and CHRs for the three name servers. What is the overall average round-trip time for domain name lookups if RTT1, RTT2, and RTT3 denote the round-trip time from HX, that means any host device, to servers DNS1, DNS2, and DNS3 respectively. What do we have here? Each one of these servers, actually particularly DNS2 and DNS3, has a table that saves the addresses in their zone. That means this table saves the addresses that can be translated directly. So DNS3, for example, will have a bunch of URLs that it can translate to IP addresses directly. In addition to this table, there is a cache. The cache saves some entries, and if an entry is found in the zone table or in the cache table, they can be forwarded to the client directly. If a query is not found either in the zone of a DNS server or in the cache, then it has to be propagated to the layer above. So when we say that DNS3 has PZ 17% and CHR 4/5, that means there is a 17% chance that a given URL will be found in the zone table. And if it is not found in the zone table, then there is a 4/5 chance it will be found in the cache. Okay. For DNS2, there is a probability 43% that the URL is found in its zone table. And if it is not found in its zone table, there is 2/7 chance that it's found in its cache. And of course, DNS2 will never actually receive a request except if it is not found in DNS3. That means it's not found in the zone table of DNS3 or in the cache table of DNS3. Then it gets forwarded to DNS2. If it is not found in DNS2, then it gets forwarded to DNS1, which has a zone table of probability 100%. That means any request that ends up going to DNS1 will be resolved at DNS1. Obviously, here there is no cache because there is no need for a cache. Anything that reaches DNS1 will be resolved from DNS1. The question wants us to calculate the average delay. So there is a round trip time from any of the host devices to DNS3. This is RTT1. Okay. Sorry, this is RTT3. If it goes to DNS2, there is RTT2, and if it goes to DNS1, there is RTT1. So, how many requests actually end up making it to DNS3? The answer is all of them. But how many of them will actually get responded to by DNS3? The answer is 17% of these 100 requests. So if we assume we have 100 requests, 17% of these 100 requests, or 17 requests, will be responded to directly, plus 4/5 of what remains from the 83%. So DNS3 will respond to 17 requests plus 4 over 5 multiplied by 100 are the requests that are not found in the zone table, but are found in the cache table. Okay, so the answer to that is 83.4. That means there are 83.4 requests that are responded to at DNS3 directly, and the RTT for those is RTT3. Okay, so if we started with 100 requests, 83.4 have already been responded to at DNS3. The remaining 16.6 have to be propagated to DNS2. And at DNS2, part of these requests will be satisfied by the zone table, and the other part will be resolved by the cache of DNS2. That means the number of requests that are actually resolved by DNS2, 7.138, which is just 43% multiplied by 16.6, the number of requests that DNS2 actually receives, plus the remainder of the requests, which is this multiplied by 2 over 7, which is the cache hit rate of DNS2. You get 9.84. So DNS3 resolves 83.4 requests. DNS2 will resolve 9.84 requests with round trip time RTT2. And then the remaining requests, which is 100 minus 83.4 minus 9.84, these are the ones that will be propagated to DNS1 and will be resolved with round trip time 1. So if you want to calculate the total average round trip time, you just multiply the number of requests by the corresponding round trip time of that DNS server, and you will get actually the average delay there. That's it for this lecture, and we will talk next time.